According to experimental result, the covalent bond between two different atoms, AB, is stronger than the average of the AA in the BB bonds. For example, the dissociation energy of hydrogen bromide is greater than the mean dissociation energy of hydrogen and bromine. To explain this phenomenon, Pauling proposed the concept of electronegativity in 1932. Electronegativity is the tendency for an atom of a given element to attract shared electrons when forming a bond. All elements have different electronegativities. A more electronegative atom exerts a greater pull on electrons than a less electronegative one. In a bond, this leads to unequal sharing of electrons between the atoms, as electrons will be drawn closer to the more electronegative atom. As a result, the more electronegative atom is negatively charged, while the less electronegative atom is positively charged. The electrostatic interaction between the positively charged and negatively charged atoms provides an additional stabilization of the bond due to the contribution of ionic bonding. The most used method of calculation of electronegativity is that originally proposed by Pauling. This gives a dimensionless quantity, commonly referred to as the Pauling scale. The dissociation energies are expressed in electron volts. The factor eV to the power of -1/2 is included to ensure a dimensionless result. Hence, the difference in electronegativity between hydrogen and bromine is calculated to be 0.73. As only differences in electronegativity are defined, it is necessary to choose an arbitrary reference point to construct a scale. Hydrogen is chosen as the reference as it forms covalent bonds with a large variety of elements. Its electronegativity is fixed at 2.20. The decision which of the two elements is more electronegative is usually done by other means. For example, according to chemical intuition, hydrogen bromide dissolves in water to form hydrogen cations and bromine anions, so it may be assumed that bromine is more electronegative than hydrogen. Thus, the electronegativity of bromine is determined to be 2.93. Electronegativity is not a property of an element alone, but rather a property of the atoms in heteronuclear molecules. Even so, the electronegativity of an element is strongly correlated with its first ionization energy and slightly correlated with its electron affinity. The element which can easily attract electrons but hardly lose electrons usually has high electronegativity, vice versa. As a result, electronegativity generally increases from left to right within a period, and decreases from top to bottom in a group. For example, fluorine on the upper right corner of the periodic table has the highest electronegativity of 3.98. On the other side, cesium on the lower left corner has the lowest electronegativity of 0.79. Because electrons are negatively charged, the unequal sharing of electrons within a bond leads to the formation of an electric dipole, a separation of positive and negative charges. The dipole moment is calculated by multiplying the amount of charge separated and the displacement from the negative charge to the positive one. In other words, from the more electronegative atom to the less electronegative one. All heteronuclear bonds have non-zero electric dipole moments. Bond polarity is typically divided into three groups that are loosely based on the difference in electronegativity between the two bonded atoms. Nonpolar bonds generally occur when the difference in electronegativity between the two atoms is less than 0.5. The charge separation in nonpolar bond is weak so that the bonding energy is predominantly due to orbital overlap or electron share. The dipole moment of a nonpolar bond is small so that its contribution to the properties of the molecules is negligible. For example, the electronegativities of bromine and chlorine are 2.96 and 3.16, respectively. Thus, the bromine chloride bond is nonpolar because it possesses a difference of 0.2. The dipole moment of bromine chloride is very small. The separated charge is only 0.066 electron. Hydrogen-carbon bonds are also typical nonpolar bonds. Polar bonds generally occur when the difference in electronegativity between the two atoms is roughly between 0.5 and 2.0. The charge separation in polar bond is significant so that the bonding energy is due to both electron share and ionic bonding. The dipole moment of a nonpolar bond is great enough to alter the properties of the molecules. For example, the electronegativities of hydrogen and chlorine are 2.20 and 3.16, respectively. Thus, the hydrogen chloride bond is polar because it possesses a difference of 0.96. The dipole moment of hydrogen chloride is larger than that of bromine chloride in despite of a smaller molecule. The separated charge is 0.302 electron. The terms polar and nonpolar are usually applied to covalent bonds, where less than a single electron is transferred between atoms. Ionic bonds generally occur when the difference in electronegativity between the two atoms is greater than 2.0. The difference between electronegativities is large enough that one atom takes one or more electrons from the other, so that the bonding energy is predominantly due to ionic bonding. The substances bounded with ionic bonds are ionic compounds. For example, the electronegativities of sodium and chlorine are 0.93 and 3.16, respectively. Thus, the sodium chloride bond is ionic because it possesses a difference of 2.23. Every chlorine atom takes one electron from a sodium atom to form a chloride anion and a sodium cation. In gas phase, the sodium chloride molecule has a very large dipole moment. In solid phase, sodium chloride forms an ionic crystal. The total dipole moment of a molecule may be approximated as the vector sum of the individual bond dipole moments. A polar molecule has a significant net electric dipole moment. For example, hydrogen chloride is polar because it contains a polar hydrogen-chlorine bond. The water molecule contains two polar hydrogen-oxygen bonds in a bent geometry. The bond dipole moments do not cancel, so that the molecule forms a dipole with its negative pole at the oxygen and its positive pole midway between the two hydrogen atoms. The ethanol molecule contains nonpolar hydrogen-hydrogen and hydrogen-carbon bonds. They do not have significant dipole moment. In addition, the ethanol molecule also contains polar hydrogen-oxygen and carbon-oxygen bonds, whose dipole moments do not cancel, so that ethanol is polar. A nonpolar molecule has a negligible net dipole moment. For example, oxygen molecule is completely nonpolar because it only contains a nonpolar oxygen-oxygen bond. The propane molecule contains nonpolar carbon-carbon and hydrogen-carbon bonds. The net electric dipole moment is very small, so it is considered nonpolar. The carbon dioxide molecule has two polar carbon-oxygen bonds, but the geometry of carbon dioxide is linear, so that the bond dipole moments cancel and there is no net molecular dipole moment. So, carbon dioxide is completely nonpolar. Carbon tetrachloride is also completely nonpolar because the four polar carbon-chlorine bonds cancel out each other due to its tetrahedral molecular geometry.